Greetings. So, we are well into our discussion on quantum physics, and although we think that it is weird, we discussed some weird sort of phenomena in our previous discussions. But slowly we have to begin to believe that it is quantum theory which gives you the correct description of nature, and it was classical mechanics which was weird in some sense, weird only because it seemed to work, and we discussed some of the reasons why it worked. Means a Renfest theorem was one such illustration which accounts how and why classical mechanics works. And quantum theory in the last century, it's a 100-year-old theory. And these are the pictures of some of the main contributors to the development of quantum theory. And you have the Broglie-Schrödinger formalism, and then another which came out of what is called as the three-man paper, Heisenberg, Born, and Jordan. So this is the Heisenberg method. And then you have the wave mechanics on one hand, and then the matrix mechanics on the other. And we're going to discuss a third approach to quantum mechanics, which is Feynman's path integral approach. So the two formalisms, wave mechanics and matrix mechanics, and later on Dirac and von Neumann consolidated that into a common scheme and pointed out that both of these are sort of representations of a fundamental theory, which is quantum mechanics. But there were many arguments between the two alternative developments, and Schrödinger, for example, said that he knew about Heisenberg's theory, and he says that I knew of this theory, of course, but I felt discouraged, not to say repelled, by the methods of transcendental algebra, which appeared difficult to me, and by the lack of visualizability. So this was Schrödinger's objection to Heisenberg's formalism, but Schrödinger himself also established the equivalence between the two, but he was very critical of the Heisenberg approach. And Heisenberg responded to this: the more I think about the physical portion of Schrödinger's theory, the more repulsive I find it. What Schrödinger writes about visualizability of his theory is probably not quite right. In other words, it is crap. So they were both quite critical of each other's approach, and Feynman came up with a different approach, which is again equivalent to the previous two. So all the three approaches, formalisms, are completely equivalent to each other. And to begin to talk about Feynman's approach, we just talk about the path an object would take if you pick up an object and just throw it in the gravitational field of the Earth and ask what will be its trajectory, all right? And we all know the answer, that it will be a parabolic trajectory. It is not one of the other trajectories which you could have thought about. Okay, means why not? Means what stops you from imagining that yes, it can take some other trajectory, like the one shown in the red, or another one, or another one, and you can think of some other trajectories between point A and point B from the start to the finish, and ask which of these is the correct trajectory. So we know the answer, that the correct trajectory is this parabola, and the reason we know it is correct is because the kinetic solution to the equation of motion has a quadratic term in, right, and then it gives you the correct force which is the gravitational. So the acceleration is always g, and it is because of this parabolic time dependence that you get this solution to be a parabola. Now, how do you solve this equation of motion? You solve it by setting up the equation of motion and putting the initial conditions on position and velocity. Now, what if you choose some other conditions? Instead of two initial conditions, you take one initial condition and one final condition. What is the position at time t1 and what is the position at time t2, which is the finish time? And you know these two positions. And then you ask what would be the trajectory. Okay? So, that is another way of solving it, and the solution to that comes from the variational principle, that the solution, the trajectory is such that it will be an extremum of action. Okay? That is the trajectory the system would take, and that gives you the correct solution. So, you have this Lagrange-Hamilton approach, and the Newton's formalism is consistent with that. And basically what we are addressing a fundamental question, whether it is a classical or a quantum mechanical problem, that what is the trajectory, how do you describe the state of a system and what is its trajectory, or in other words, how does the state which describes the system, how does it evolve with time? In quantum mechanics it will not be a trajectory, but it will be an evolution of the state vector, right? And then we should then ask as to why does Newton's second law work, because it also gives you the correct trajectory. So, it seems to work, and we should then ask that, okay, if quantum mechanics is the correct formalism, then why is it that Newton's equation is giving you the right solution which does not take into account quantum effects? So, the Feynman approach, or you can even call it as Dirac-Feynman approach, because it is based on an original idea which was given by Dirac. This provides some sort of an insight into this issue as to why classical mechanics gives you a reasonable approach. So, Newtonian approach is so much inspired by the idea of force as the cause of change in equilibrium. So, equilibrium is described by constant momentum, and when it changes, it does so at a rate which is equal to the stimulus, which is the cause, and acceleration is what it results in, and there is a linear relationship between cause and effect. So, that is the heart of Newtonian mechanics. So, the principle of variation makes no use of the idea of force, okay, but it gives you the same answer as Newton's mechanics does. And the principle of variation, Hamilton's principle, it rests on an ansatz that, okay, it is the action which is the definite integral of the Lagrangian from an initial time to the final time, that this is what is called as action, and this action is an extremum. It is stationary. So, that is the ansatz that you make, and if you then ask what should be the Lagrangian, then you expect the Lagrangian to depend on the mechanical properties which are position and velocity, right, which describes the state of a system, and you expect it to depend on quadratically on the velocity, so that there is isotropy. So, if you set up the Lagrangian as t minus v, which has got these properties, then automatically the condition that this is an extremum, and this is what we discussed in our earlier discussions on classical mechanics, that the condition that action is an extremum is that a certain equation is satisfied, and that equation is nothing but the Lagrange's equation, which you have in this red box. And if you see, you can sort of identify the del L by del Q with minus del V by del Q, which in Newtonian sense is the stimulus force. and this is the rate of change of the generalized momentum in classical mechanics, which is the partial derivative of the Lagrangian with respect to the generalized velocity. So, now you see the correspondence, and this explains to us as to why is it that Newton's equation actually works. In some sense, yes, both can be considered to be equivalent, but I am trying to lead you to thinking that the principle of variation in some sense is more fundamental. Although one can argue that Newtonian formulation is equally fundamental, they are after all equivalent, they give you the same results. So, it does not make too much sense to say that one is more fundamental than the other, but in my mind it is useful to think of the principle of variation as more fundamental, because as we are going to see, it also provides a basis for quantum mechanics. Okay? That is what we are going to discuss in this class. So, you have this Lagrange-Hamilton approach, which is contained in the Lagrange's equations, and then you can formulate it in terms of position and momenta, and then get it in terms of Hamilton's equations, which also give you the same solutions. So, the Lagrange-Hamilton formulation is completely equivalent to the Newtonian formulation, and the reason is that the interpretation f equal to p dot dp by dt, it is very consistent with Lagrange's equation, which is del L by del Q equal to d by dt of del L by del Q dot, which is actually the same equation, right. So, now you think about possible trajectories. You know the position. I said that you take one initial condition and one final condition. The initial condition is that you know the position at the start and you know the position at the end, and in between the trajectory is something that you want to determine. You can determine this trajectory from the forces by integrating Newton's second law, or else by solving Lagrange's or Hamilton's equations, either which way, right. And you have infinite possibilities. You can think of arbitrary number of trajectories which go from start to finish, all right. But out of these there is only one that the system will actually take, and that is what is correctly described by the principle of variation. So, the principle of variation is not telling you the reason why the system takes that trajectory. It describes the trajectory which is chosen by nature. So, it provides you the correct description, and again I am trying to emphasize here that you are answering how does the system evolve and what is the correct description of the evolution of the state. You are not answering why is it that it does this. You can't say that this is because of Lagrange's equation. If there was no Lagrange's equation, the system would have still done that, right. So it's not because of the Lagrange's equation. So, in quantum mechanics also sometimes when you are not able to get simultaneous information about incompatible observables, sometimes you think that it is because of the uncertainty principle. No, it is not that. It is because you are not able to make compatible observations of certain observations, right. Newton's law does not provide a correct description, classical mechanics does not provide a correct description, and the Heisenberg principle of uncertainty gives you a correct description. So, it tells you what is the law of nature, not why is the law of nature what it is. Okay? So, the focus is on what and how and not why. So, there can be alternative trajectories that you can think about, and Saurav and I were discussing this figure yesterday, that you have got a continuous trajectory which you think may be the one, or maybe the dashed one, or maybe the dotted one. Now, the dotted one is obviously absurd because it goes to negative time, and then it shows you possible two positions at the same time, which is not a classical idea. So, it is unphysical in some sense, but that does not mean that the trajectories which do not have such a loop are physical. They are also unphysical, and you can think of infinite trajectories between start and finish which are not obviously unphysical, nonetheless they are also unphysical. What the trajectory which nature picks is described correctly by a particular trajectory for which action is an extremum. Okay? So, there are many curves which can be plotted, but only one for which action is an extremum is what nature picks, and that is the solution to the problem. And in fact, this was the problem which was posed by Bernoulli. He asked what is the brachistochrone from a start to the finish if an object was to roll down under certain constraints, but only under gravity. So, that was the question, and the solution which Newton gave was that it is the brachistochrone. So, there are many shapes that you can think of, and we have discussed this figure in one of our earlier discussions. So, here is a model of the brachistochrone and some other trajectories which can be shaped, because depending on how you shape the slope, right, you can come up with infinite number of possibilities. Out of this, the fastest that an object can roll down from point A to point B is given by a particular shape which is the brachistochrone, which turns out to be a cycloid, and that is the trajectory that we can get by applying the principle of variation, right. And this is a very fundamental principle which I think in some sense, although equivalent, it is like saying that okay, two things are equal, but one is more equal than the other. So, the principle of variation and Newtonian methods in my mind are more equal, are both equal to each other, but the principle of variation is, I would say, more equal, all right, if you will allow me some play with this. So, here are references to some very good papers which recommend that the variational principle really needs to be taught early on in college education, all right, which are nice to read. And now that we have dispensed with the idea of force in Lagrangian and Hamiltonian mechanics, as a matter of fact, you dispense with the idea of force even in general relativity in classical mechanics, okay, because then gravitational attraction is seen in terms of curvature of space rather than a force which is acting, okay. But then classical mechanics seems to work, and we first argued that okay, Newton's law seem to work even when you have to dispense with the idea of force, even in classical relativity, right. You do not need quantum mechanics to dispense with the idea of force. So, why does it work? Okay. So, we have found a partial answer that okay, it seems to work because it is compatible with the principle of variation. Okay. So, that is a comforting idea. But now you can ask, why does the variational principle, why does the Lagrangian and Hamiltonian principle work? Because both rest on the idea that position and momentum are simultaneously determinable, right. The equations of motion, Hamilton's equations of motion are for q dot and p dot, and they would make no sense if you could not determine q and p simultaneously. And once you reconcile with the fact that okay, q and p are not simultaneously determinable, then you should ask why does the principle of variation work in classical mechanics. And then we get some insight into this situation by now recognizing that the Lagrange-Hamilton principle, the principle of variation, turns out to be an excellent approximation to quantum mechanics, which is described by the same principle of variation, okay? And this is the formulation by Feynman based on an idea which was given by Dirac. And Feynman writes over here that when he was in high school, his teacher, Mr. Beda, told him that, okay, you are looking bored, I want to tell you something interesting. And he talked about this trajectory of an object which is tossed and then how does it fall, and how the principle of variation gives you the correct trajectory. So this was the problem that they discussed, and this was this set Feynman thinking about the principle of least action, or the extremum action as it should be correctly called, and he went on to develop the path integral approach to quantum mechanics, which is based on an original idea due to Dirac, and it allows a backward integration of classical mechanics as an approximation to quantum mechanics, which is the correct theory of nature. All right. So, this is a reference to the first suggestion which was made by Dirac, and it is also discussed in Feynman's thesis, and it was based on this principle of least action, and it was an attempt to describe the evolution of the quantum of information in a wave packet. So, what is this approach? This is a very fascinating approach, and this is summarized in Feynman's Reviews of Modern Physics paper 1948. And we see that, okay, from classical mechanics you can go to quantum mechanics through the wave mechanics of de Broglie Schrodinger, or the matrix mechanics of Heisenberg, Born, Jordan, or the Feynman path integral approach, and it all leads you to one theory, which is the quantum theory. And in Feynman's abstract, he mentions that it is a formulation of quantum mechanics, non-relativistic quantum mechanics, in a different way. It is, however, mathematically equivalent to the familiar formulation. The familiar formulation he is referring to the de Broglie Schrodinger and Heisenberg formulation, right? It is equivalent to that. And in this formulation, the probability that a particle will be found to have a path x as a function of t lying somewhere within a region of space time is the square of sum of the contributions, one from each path. So, this is the ansatz, this is the premise of the reformulation of quantum mechanics. And then the contribution from a single path is postulated to be an exponential whose phase is the classical action. Now, this is the same action as we are familiar with from the principle of variation, the Hamilton's principle of variation. Okay, it is the same action, it is integral L dt, where L is the Lagrangian, it is the same action. And then the total contribution from all paths reaching a certain destination is given by the wave function, which satisfies the Schrodinger equation, and the formalisms are equivalent. Now, this is what summarizes Feynman's contribution. All right, each contribution is a certain probability amplitude, which is the wave function. And it is interesting to note that Feynman's first paper was rejected by Physical Review. That does not mean that every paper that is rejected by Physical Review will have the same fate as Feynman's first paper. So, be warned about that. And everything that is done using path integrals in quantum mechanics can actually be done using the conventional or the familiar Schrodinger-Heisenberg quantum mechanics. Okay? So, it is not that it is enabling you to do something which the Schrödinger-Heisenberg formalism did not allow you to do. However, once you get into quantum field theory, then the path integral approach turns out to be much more powerful. Okay? So, that is where its power really is sensed. In other applications, you might actually choose the Schrödinger-Heisenberg conventional approach, which is why that is the method which is normally discussed in most courses, because that gives you equivalent answers and perhaps in a much more simplified manner, but not so once you get into quantum field theory. So, we begin with the discussion on the Young's double slit experiment, all right, and this is something which runs through the discussion on quantum mechanics. And you can have two slits, right, and you can have light or electrons depending on what you are shooting to go from window 1 or window 2, and then you have a superposition between this, and then this is the solution that we have discussed, and this is quite correct, but not fully accurate actually. So, we have used this even in our earlier discussions. We even discussed the quantum eraser and other phenomena using the double slit experiment, nothing fundamentally wrong with that. But then if you are asking is it completely accurate, it is not, because the principle of superposition is fundamentally correct, but it requires you to use the boundary conditions fully, and the boundary, there are two boundary conditions that we have used here. One is that one of the slits is open and the other is both the slits are open, right, and then once slit 1 is open, once slit 2 is open, and the third is when both the slits are open. So, there are three things that you must consider, and if you consider these three things which are not considered in the usual analysis of the Young's double slit experiment, you get a slight correction which we have ignored, but that can be taken into account, and that is the work of this Sinha paper that we talked about a little earlier, that they take into account all the boundary conditions comprehensively, use the Feynman path integral approach, and they get this correction, and I believe this has also been the consequences. There is absolutely no classical analog to that, and there have been some experiments which give you absolutely mind-boggling trajectories which have also been seen in a laboratory. But the main features of quantum mechanics are understood even if you do not take all the boundary conditions, but take the major subset of the boundary conditions, which is what most of the discussions on the Young's double slit experiment are, and that is also what we shall restrict ourselves to. So, suppose you have a third slit, right. Now, you have alternative paths. You can insert another screen with two slits, and now think of alternative paths. Okay. Now, look at this, there are these alternatives also possible. There are some more alternatives, right, and some more, and some more alternatives, and some more, right. Now, what if you insert some more screens and then make more and more slits in it, right. So, you are getting lots of additional possibilities, and you will have to take into account all of these, okay. And all the paths need to be summed over. Okay? All the paths need to be summed over. I think there is a typo here. This should be D and not R. Okay? So, you have many possibilities. So, let us think of some more possibilities. So, you have a possibility that an object is scattered by the screen, then it finds its way to an obstacle on Mars, then goes to some other galaxy and finds its way back through one of the slits, right. And if you want to consider all the possibilities, yes, what stops you from considering this, right. So, there are these additional possibilities and you cannot dismiss them, and you will have to add up all the possibilities. Now, you can of course ask that the light or the particle would have already reached the detector, it is only few centimeters away from it, and this particle is going to take a few light years to go to another scatterer in some other galaxy, which is a few light years away. Even the sun is more than 8 minutes away. So, it is going to take that much time, but this particle would have already reached. So, how much time would it take? Now, that depends on the velocity of that particle, right. And you certainly know that nothing is going to move faster than light, right. But that question becomes irrelevant, because if you are now talking about the path that it has taken, the trajectory, where was it and when was it, you are trying to answer both the questions, right, because the speed is going to determine when the particle would be at that point. So, you are answering both when and where, and quantum mechanics does not answer that. It tells you what is the right question to be asked, okay? Because only a measurement would give you that information, not speculation. If you did a measurement, the system would collapse into an eigenstate of that measurement, but otherwise it remains a possibility which you have to take into account, all right, no matter how absurd it seems like, okay. So, the speed of the particle of these Feynman particles, all right, of these infinite paths that the object can take is not a question you have to worry about, because you know that position and momentum are not simultaneously determinable. So, you are not required to answer when and where, since you know that they are basically sort of orthogonal. Complete knowledge of one destroys information about the other completely, right. So, you have all possible trajectories, including the particle traveling through space and getting back, right. And we can ask, does the particle actually take these complicated paths? And we really do not know. We can answer it only if we do a measurement. If we did a measurement, you will get an answer. That will be like doing the which way experiment, and you will lose the interference. So, that is a price you have to pay for this knowledge, all right. So, the measurement is what pushes the system into a possible eigenstate. Now, this figure is a little bit misleading, because it has some curvatures which are really not quite correct. The actual paths do not have curvatures of this type, they cannot, because in between quantum scatterers the particle must go in a straight path. So, this curvature would be correct only if there are scatterers at infinitesimal distances from each other. So, it is not inaccurate, but it is not correct if if there is a finite distance between scatterers, because between finite distance between the scatterers, the Feynman particles would go in straight lines. Now, this is an important point to remember. Okay? So, now to discuss this further, we will consider motion in just one dimension. All right? So, we think about a particle which can move only on this black line, all right, along, let us say, the x axis. The particle starts at x0 at time t0, and at a later time t prime, which is greater than t0, it is at the finish point, which is x prime t prime. How does it get there? If you want to consider alternative paths, you have to consider the possibility that from x0 t0 it jumps to this first blue dot, then to the other blue dot, first to the upper blue dot, then to the lower blue dot, and then goes to the finish. It could also first jump to the lower blue dot and then to the upper blue dot and then go to the finish, right. There are alternatives that you have to think about, right. It can also jump to the lower, what is that color, orange maybe, brownish, I do not know, orange, let us say, right. It jumps to this orange position and then goes to the finish. So, there are various possibilities, in fact infinite, and what we will do now is to sweep this figure from left to right as time increases. Okay? So, this very figure, these very jumps will be shown on a two-dimensional diagram in which you sweep this from left to right. So, from x0 to 0, the particle jumps to this point, then to this point, and then to the finish point. This is one path. The other path is that it has jumped to this orange point and now goes to the finish. So, these are the possible trajectories in a space-time diagram. Okay? And there are infinitely different paths which are possible, and you need to consider the probability amplitude for all of these paths and then sum over the amplitudes, which is also sometimes called as summing over all the histories, because once it reaches the destination, how it got there is its history, and you must sum over all possible histories. Okay? So, this is this Feynman approach, or what Feynman called as the space-time approach to non-relativistic quantum mechanics, which is documented in his article Reviews of Modern Physics. All right? And then he considers the probability amplitude for each path as a complex amplitude, and then sum over all the histories. So, the probability amplitude, the propagator for the particle to go to the finish point xf at time tf, is then given by all of these, and you have to take into account all of these. All right. So, if you just take two steps, then the lower equation gives you that possibility, right. So, you have got one intermediate hop and then you go to the finish, but you can have infinite hops any which way. So, this is the Feynman approach, and I will stop here. If there are some questions, we can discuss. Otherwise, we will continue from this point in the next class.
The Mitchell experiment.
Yes.
And we also talked about the delayed choice.
Yes.
So suppose we are conducting an interference experiment like that, and unintentionally or unknowingly there are some scatterers away from it, which can be a possible kind of delayed choice. So in that case, we won't be getting the pattern.
Yeah, means the presence of getting that information. So, if you remember that equation that we had in the previous class, you have a marker. Whether you have set it up deliberately or not is not relevant. If there is a marker, then the Hilbert space gets expanded by the state vectors of the marker, and the marker states are orthogonal. So, the interference is lost. That is the reason I had that picture, that cartoon of a girl blinking. So, whether you see it or you do not see it, or you see it now or you see it later. Okay? If there is a marker, you have an orthogonality, and that orthogonality destroys the interference. So, if you go back to the previous class and go through this discussion again as to how the markers destroy the interference, and that is what happens in quantum theory. It is because you have to admit that the system has to be described by a vector in the Hilbert space, but the Hilbert space is no longer what it was if there are marker states, right? Thank you. Any other question?
Sir, like in Feynman path integral, we will be having like n possible number of paths for a particular experiment, let us say, but there will be only one correct path which it chooses. Is there any way while summing up all the others get cancelled?
No,
it's
there is
just
only one particular path, is the classical description. In quantum mechanics, all of these paths have to be taken into account to get the correct intensity. The path is unique in classical mechanics, not when you do the formalism correctly, which is the quantum mechanical way of doing it. You must sum over all the paths. You cannot, only when you sum over all the paths do you get the correct description. If you leave out some of the paths, then you do not get the correct description. And that is the problem with the usual interpretation of the Young's double slit experiment, which I mentioned, that the boundary conditions, when you have one slit open or the second slit open or the third boundary condition that both the slits are open, right, are somewhat tricky. And once you take all of these into account, then you get a small correction to the usual interpretation of the Young's double slit experiment. Now, that is a relatively minor effect because the corresponding probabilities are low, but not 0, and they are in fact detectable. So, you do have to take into account all of these paths, not just one of these. But what we are going to discuss is that why that one particular path in classical mechanics turns out to be a good approximation to this. Okay. So, what we will learn in the next class is that all of these alternative paths, they come with their own phases. Okay. And when you have two amplitudes with different phases, the interference can be constructive or destructive, and all of these alternative paths tend to cancel out in classical mechanics, giving you a single path, which is the Lagrange-Hamilton path, when action is much larger than Planck's constant. That is why classical mechanics turns out to be a good approximation. So, you get one trajectory in classical mechanics because the nature admits all of these infinite paths. But when action is much larger than the Planck's constant, all of the phases of the other paths they cancel out, leaving you with only one. Yeah. Thank you. We are going to discuss this in the next class.